So, better decisions with machine learning. So this is actually, it's going to be about machine learning, but it's going to be about how you can better use classifiers in machine learning. So if there is one message here, then it is you should, first of all, whenever you take decisions, you should do that on the basis of probabilities. And whenever you use probabilities, you need to make sure that they are calibrated. And I'm going to say a bit more about why and what that means for probabilities to be calibrated. This is a very old topic that keeps being forgotten and rediscovered in machine learning and AI. So I'm kind of a bit on a mission to make sure that people are aware of the issues surrounding this and what is important. So just to set the stage, here's a simple decision problem. So I live in Bristol. I have, by bicycle, I have a commute for about 20 minutes. I'm cheating now because I have an e-bike, but it's still, Bristol is very much up and down, so it's about 20 minutes. So when it's raining, I can cycle in the rain, or I can take the bus. Okay, so I could make that into a cost-sensitive decision problem. So let's see what are the costs that are involved. So I have the cost of a bus ticket that I have to pay when I take the bus, or that I don't have to pay when I cycle. There's the cost of cycling, which actually in my case is a negative cost. It's a benefit. I like cycling, so there's a cost of not cycling. So this would be a negative cost. There's the cost of rain in the sense that, you know, people are a bit less happy when it rains, so there's a cost involved with that as well. There's a cost with getting wet when I'm cycling, not when I take the bus. And then we have a table like this. It rains with a certain probability p. It doesn't rain with the probability 1 minus p. And then these are my decisions that I can take. I can either decide to take the bus. I can decide to cycle. If I take the bus, I have the cost of a bus ticket. In this column, if I cycle, I have the cost of cycling. If I cycle and it rains, I have the cost of getting wet. If it rains, I have the cost of rain, and so on. So then I can look at, and you know all this, I mean, this is what you would do. There's nothing very deep here. But in each of these decisions that I can take, I have an expected cost. Okay? And then I can take a decision. I can say I would cycle if the probability of rain is less than this value here. Okay? And notice that, of course, the cost of rain disappears because that isn't dependent on my decision. So if it rains, then I incur that cost. If it doesn't rain, then I don't incur that cost. So just to verify this, let's put a few numbers in here. So let's say the cost of a bus ticket is 3. The cost of cycling is -4, so I like to cycle. Cost of rain doesn't matter, so I could as well set it to 0. Cost of getting wet is 10. If I stick these numbers in, then the decision threshold is 70%. So if the forecast is rain with more than 70%, I'm going to take the bus. If it's less than 70%, I'm going to going to cycle. Just verify that a little bit more. How do I get this p equals 70%? Well, if I set p equal to 70% and I plug these numbers in, then the expected cost in both columns is the same. Okay? So if I change the numbers, for example, I really, really dislike getting wet, so I increase that to 20. Then I will take the bus if the forecast says chance of rain larger than 35%. Okay? So this is very straightforward, but this is kind of underlying a lot of the stuff that we do in classification and machine learning. So this only works if I have calibrated, reliable probability estimates. And that's what machine learning models do. They try to estimate as accurately as possible these probabilities so that I can take optimal decisions that minimize expected cost. Okay, so here is a verification of that you still get the same expected cost if in this setting if the probability is 35%. Okay, so the general formula, if you have these 4 cost parameters, is this. Doesn't really matter, but the key point is that there's only 1 degree of freedom here. So you have 4 cost parameters, but in the end, for decision-making purposes, there's only 1 degree of freedom, and that is in terms of this ratio of differences. Okay, so you can normalize this. So for example, you can adjust these costs such that the perfect classifier always has cost 0 rather than a negative cost. You can set it. So basically what you do in each row, you subtract. In this row, you subtract C1. In this row, you subtract C4. You can do that. Then you get this table. The decision rule doesn't change. Okay? Or you can even normalize this one to the value 1. So you divide everything by this quantity. Then you get 1 here, and you get this ratio here. And that is the 1 degree of freedom that you have in this setting. Okay, this is all well-known box standard decision theory. Okay, but this is kind of underlying. This is a kind of motivation what we can do if these probabilities are reliable. Now, why do I go on about this? Well, because there are many machine learning methods that we know give unreliable probabilities. Let me give you 2 examples. One of them is the well-known and well-loved naive Bayes classifier. So this is used a lot in spam email filtering, for example. What's wrong with naive Bayes? Well, it makes these independence assumptions. So it sort of assumes that the probability of observing the word Viagra in a spam email is independent of the probability of observing the term blue pill in the spam email. Clearly, these are not independent, meaning that if I observe the word Viagra, I'm expecting the word blue pill as well. So blue pill doesn't give me a lot of extra evidence. Naive Bayes ignores that, just assumes that they're independent, and therefore gets overconfident. It overestimates the probability. Something similar happens actually with boosting, for example. Because boosting, you have an ensemble of classifiers. And the way that boosting combines the votes from the classifiers, it assumes that they are independent, which they are clearly not, because the next round of boosting is trained on the mistakes of the previous round. So clearly they are dependent. So boosting also tends to be overconfident. Okay, and I will get back to that point. Okay, so this is kind of an outline of the talk. So I'm going to spend most of the time discussing 2 papers and associated work. So this is work that we had published in AI Stats in 2017, and there's a follow-on journal paper there, and we have continuing work on that, which will be presented at NeurIPS this year. This is an older paper which actually looks at the case where we don't use accuracy as an evaluation metric in our classifiers, but we use the F measure of or the F score or the F1 score. Can I see a show of hands? How many of you know or have used the F measure in their work? Okay, that's pretty good. Okay, good. So, and then finally, I will this is very speculative, but I will talk a little bit about where I see this going. So let's get started. So I will start with an introduction about ROC curves, receiver operating characteristic curves. Can I see a show of hands? Who of you knows what a ROC curve is? Okay, very good. But if you don't, I'm just keeping it very, very simple. So here is a brief explanation of an ROC curve. What you see here is a very simple decision tree. I like trees. Whenever I don't understand something, I go back to trees and try to figure out how it works with trees, and then work from there. So very simple binary decision tree. It doesn't really matter what A and B stand for, but we have basically, to make matters easier for me, I've sort of made the case such that these leaves of the tree, there are 3 leaves, and they're left to right, they're ordered from mostly positive to mostly negative. Okay, that's of course not in general the case, but that's just to make my life easier. Yeah, so in this case, we have 6 positives, 1 negative. Here we have 2 positives, 1 negatives. Here we have 2 positives and 8 negatives. So now what could we do with this? What decisions would we take in these leaves? Well, obviously, one thing we could do, the most obvious thing, would be majority class, right? So we would label this plus, plus, minus. But it's also clear that we lose information there because this one is much more plus than this one. So probably we don't want to label it just with classes. We want to label it with probabilities. But then the question is, what probabilities? I'm going to spend the next couple of minutes to make something very simple complicated, okay? So bear with me, because of course, what would you do? Well, you would probably predict 6 out of 7 here. You would predict 2 out of 3 here, and you would predict 2 out of 10 here, right? And that's what's going to be the outcome. But I will say a little bit more about that, and that's important because if we, at the moment, we are interested in accuracy. When we're interested in F-score, things change quite a lot, and that's not well understood. Okay, so this is kind of a stylized ROC curve. If you've seen that before, then you know that we have the true positive rate here, the false positive rate here. So performance on the positives here, performance on the negatives here. For some obscure reasons, good performance on the y-axis is here and good performance on the x-axis is here. It would make much more sense if you have true positive rate here to have true negative rate here, but that's not how people do it, because maybe they like increasing curves more than decreasing curves. Or you could have false negative rate and false positive rate here. Anyway, this is the convention. And the way I think of this, if you have, particularly if you have trees, if you have 3 leaves, you have kind of 3 segments in that curve. And we have 3 of these line segments, which clearly map to the numbers over there. But also what's important, you have 4 operating points of this classifier. And the operating points could be visualized this way. If you read the leaves from left to right, then you could label every leaf as negative, then you get the always negative classifier. The always negative classifier does fantastically well on the negatives, but it does fantastically not well on the positives. Okay, so the always negative is here. Similarly, the always positive is there. And then you can have plus, minus, minus, and you have plus, plus, minus. Okay, and each of these give you a particular true positive rate and false positive rate. Okay, and so the majority class classifier is here. Okay, plus, plus, minus. That's this one. And under the assumption of equal class distribution, that is indeed optimal. And one way to see that is that actually, so these lines are iso-accuracy lines. So they connect points with equal accuracy. So if I have uniform class distribution, if I improve performance by 1 on the positives, then I need to decrease performance by 1 on the negatives in order to keep my accuracy the same. So these are 45-degree lines if I have equal class distribution, but the slope of the lines changes if my class distribution changes. Okay? So the thing that you already did in your head, which was majority class, is optimal under the assumption that I have an equal class distribution and under the assumption that my misclassification costs on the classes are the same. Okay, so I will often assume class distribution and unequal misclassification cost as 2 sides of the same coin. Okay, so you have reasons to do better on the positives than on the negatives. That might be because there are simply more positives than negatives, or it might be that mistakes on the positives are more costly than mistakes on the negatives, right? So there's 2 sides of the same coin. So how does this change if I change the class distribution? Well, a simple way to do that is just to manipulate the class distribution. So suppose in this case, I call this Z, which is the deployment class distribution. So now I'm assuming that only 1 out of 3 instances is positive, not 1 out of 2. So what I've done here is double all the counts for the negatives. Okay? And that doesn't change the ROC curve. The ROC curve, because the ROC curve is formulated in terms of true positive rates and true negative rates. So the rates stay the same if I change the class distribution. But it changes the slope of the iso-accuracy lines. Okay? So now, because I have more negatives, those lines become steeper. And the way I think of that, if steeper lines kind of pull me in this direction, which is the always negative classifier, right? So it's more of a force pulling in that direction. So now something interesting happens. Because actually this leaf is now exactly on the decision boundary, meaning it doesn't matter how you label that leaf for accuracy. If you label this positive, you get the same accuracy than if you label this negative. Okay? So in this case, a calibrated probability estimate for that leaf would be 1/2, not what we had previously, which was whatever. Oh, we don't have the numbers yet, but previously you would predict 2/3. And so with that changed class distribution, you would label that as 1/2. So I want you to have the intuition that predicted probability 1/2 under uniform class distribution means being on the decision boundary. Now, machine learners are afraid of the decision boundary. They want to be away from the decision boundary. I think that is a mistake, because actually sometimes if I don't have a coin and I can't toss my, well, I could toss my credit card, but it doesn't mean anything. But if you toss a coin, you have very good knowledge about that coin. Assuming it's fair, your knowledge about that coin is very precise. Namely, the probability of heads is 0.5. That's not like, I don't know anything about this coin. You don't know anything about the outcome of tossing the coin. Yeah? You have perfect no knowledge about the outcome, but you have very good knowledge about the coin. So being on the decision boundary, being able to reliably predict 0.5 is a really good thing. But it's not like 0.5 is sacred or so. You also want to know where 0.6 is and where 0.7 is and where 0.8. And that's really what calibrated probabilities are about. This comes from forecasting theory. So weather forecasters have worked on this for a long time. So when a weather forecaster says probability of rain is 0.7, they don't say, well, it's a bit higher than 0.5 and a bit lower than 0.9. No, they mean that if you would collect 100 cases where the weather forecast of rain, the probability of rain is 0.7, you collect 100 cases of those, you want it to rain in 70% of those cases and not to rain in 30% of those cases. Otherwise, the probabilities are poorly calibrated. Actually, a little side story here. Weather forecasters believe that we are not very good at doing this kind of cost-sensitive reasoning, and we are not able to change our own personal thresholds. So they do it for us. So for example, weather forecasters know that people dislike the situation where it rains when no rain was forecast more than they dislike the situation when it doesn't rain when rain was forecast. That also has a cost, because you dress for rain and you carry your umbrella and then you didn't need it. So both of them have costs. They're not the same costs. Weather forecaster thinks that we can't handle that situation, which I think for most people is true. And therefore they adjust their costs a little bit. So they kind of tend to over-report the probability of rain to compensate for that fact that we are really annoyed when it rains and when it rains when it wasn't forecast. Okay, right. So here is finally, after much ado, the answer that you already would give in your head. If the numbers are like this, then these are the probabilities that you would predict. And these are calibrated. These are, in a sense, the right probabilities with this kind of knowledge that you have. And here's a formula that the nice thing about doing this is that they can be formulated just in terms of the shape of this segment. It doesn't really matter where that segment is. So I write this as delta true positive. So let me explain this a little bit. So here we have the true positives and the false positive. If I put my decision boundary here, which is everything negative, I don't predict any positives, so I don't have any true positives, but I don't have any false positives either. If I put the decision boundary here, then I accumulate 6 true positives and 1 false positive. If I slide it to here, then I accumulate 2 more true positives and 1 more false positive. If I slide it to behind here, then I have 10, 10 here, okay? And the key thing is that in order to get calibrated probabilities out of this, you only need to look at the differences between these columns, which are the numbers here already, okay? So a very complicated way just to say that these are sufficient statistics for getting calibrated probabilities out of this. But this only holds when the criterion that you're optimizing is accuracy. This will change a lot when you look at F-score, okay, which a lot of people in information retrieval do, for example. Okay, so I will get back to this picture and talk through how this would work with F-score. Okay, so there's a little bit of technical stuff in here, but I've tried to keep it to a minimum, and if you want more of the technical stuff, then here are the pointers to the paper. So a lot of people, it's very common, for example, now again in deep neural networks, but also in other areas, in support vector machines, for example. So support vector machines give you distance from the decision boundary, yeah? Positive distance or negative distance, which is some kind of geometric number on a real valued scale that is not kind of normalized in some way. So John Platt answered the question, how do we get probabilities out of support vector machines in a particular way which led to a sigmoid squashing function, okay? And this is very common now in deep learning as well. There they often call it the softmax function, which again is a sigmoid squashing function, okay. Sigmoids assume that the scores that you get out of your classifier are real valued, so have infinite support. Okay? So what should you do if the scores that are coming out of your classifier are, for instance, already naive Bayes? So they are on a 0-1 scale. They don't have infinite support. It would be actually, although a lot of people simply still use sigmoids there, it would be incoherent to do that. And I'll talk through this, why this is. So here, we come up with an alternative to that using beta distribution. So let me talk you through this. So here is, and ignore the maths, it doesn't really matter, but this is a one-slide justification of Platt scaling or logistic calibration. So that's kind of this logistic map that we have here, where on the x-axis we have the scores coming out of the classifier, and on the y-axis we have it is converted into probabilities. So here's one way of justifying it. It's not the only way of justifying it, but one way of justifying it is assuming that the scores coming out of your classifier, if you look at the histogram of the scores coming out of your classifier, and you separate it into actual positives and actual negatives, okay? So you assume some kind of shape, and you assume that the scores on the negative class are separated from the scores on the positive class. Otherwise, your classifier doesn't work very well. So your classifier tries to pull these scores apart. And if you assume that both these distributions are normal, and if you assume that they have the same variance, then you do some magic. So here are the normal distributions. You look at the likelihood ratio between the two, and because you assume the same variance, the quadratic term drops out, and you get a log linear form. And if you then convert the likelihood ratio into a probability, you get this formula, you get this form. So this is kind of your one-slide introduction why logistic scaling, Platt scaling, might be a good idea. Okay? But I have to say it's a sufficient condition, not a necessary condition. Why is that? Well, two normal distributions have, each of them have two parameters. So two normal distributions, you have 4 parameters. You're losing one of them because you're assuming the same variance, and you're losing another one because you're taking the ratio between the two. Okay, so my point is there are other distributions that will give you the same family of calibration maps. Okay, so this is all well and good, but it doesn't always work if your scores are already on a finite interval. And here's an example of that. And this is a real example from, well, real. It's probably a UCI data set, so you can argue how real UCI data sets are, but it's one of those benchmark data sets. So this is known as a reliability diagram. So I want you to concentrate on the black dots for the moment. There are 10 black dots. What have I done? I've discretized the scores coming out of my classifier in 10 bins. Okay, so the lowest bin here, then the next bin there. So these are very low. These are the 10% lower scores. These are the next 10% scores, and so on, all the way up. And on the y-axis, I've mapped the empirical probability, which means the proportion of positives in that bin. Now, if my classifier was well calibrated, those black dots would more or less follow the diagonal here. So the lowest 10% of the scores would have roughly 10% positives. The next 10% of the scores would have roughly 20% positives, or 15 if you map the middle of the bin, right? And then you would nicely follow the diagonal. These dots clearly don't follow the diagonal, okay? So what's happening with these dots, and this is actually, I think, important, so let me spend a minute to explain it. This one is okay, but there's a big jump to above the diagonal. Yeah? So what does that mean? The classifier thinks this is in the lower 20 percentile of the scores. But actually, in practice, there's something like 35% positives here. So the classifier was overconfident here. So the classifier was very confident that most of these guys were still negatives, whereas actually 35% of them were positives. So here, this is a case where the classifier is overconfident. So if a classifier is overconfident, you don't get a sigmoidal shape, you get an inverse-sigmoidal shape. Yeah? And logistic calibration can't model that. Logistic calibration has to model a logistic shape. So our alternative, which I get to in a moment, beta calibration, is able to map that inverse-sigmoidal shape. So what it does is it recognizes that the classifier is overconfident and pushes the scores back to the middle, whereas logistic calibration always pushes the scores to the extremes and would make it worse in this case. As you see, the blue line is a very poor fit. Okay? So let's give you the one slide description of our solution. It's very similar to this one, the logistic one, except that we're going to change the family of distributions here to beta distributions. Okay? So here's an example of beta distribution where clearly the classifier gives very extreme scores, very low scores for the negative class, very high scores for the positive class. And if you do the maths in this way, we have two beta distributions, the likelihoods, we do the likelihood ratio, we convert it into a probability. We get a different class of calibration maps. And this family has some very nice properties. So let me show you just graphically the properties. I want you to concentrate for the moment on this line here. Let me go back and briefly talk about the parameters. So again, the beta distribution has two parameters. So two beta distributions, 4 parameters. I don't have to assume anything about the relationship between the two distributions. So I don't have to assume equal variance or whatever. So I don't lose that 1 degree of freedom, but I do lose a degree of freedom because I look at the likelihood ratio. So this family ends up with 3 parameters. Yeah? Logistic had 2 parameters. So the logistic parameters are basically where is the midpoint for p.5. You can shift that around, and also it has the parameter what's the slope at the midpoint. These are the two parameters of the logistic function. We have three parameters. Okay, so the parameters are shown here. We have A, and I'm showing it for three values. We have B, and we have the midpoint. So in each panel, we show three possible midpoints. So if I want you to concentrate on the A equals B diagonal for a moment. So this kind of means A equals B means that the two beta distributions are each other's mirror image. So that's sort of what happens in the negative class is kind of a mirror image of what happens in a positive class. And that gives kind of symmetric curves, including the kind of sigmoid curves that we have here, but also the inverse-sigmoidal curves that we need for things like naive Bayes and boosting. And very interestingly, this family includes the identity map, which means that if I use this as a post-calibration method, this method would recognize that my classifier is already calibrated and just leave the scores alone and just say the calibration map is the identity map because there's no work for me here. If you did the same thing with Platt scaling, it would do something and it would make it worse because it doesn't have the identity map in its family. Right? So we have the two advantages. One is that we have sigmoids and inverse sigmoids, and we also can recognize that our classifier is already calibrated. Okay, there's a very nice way of implementing this. And again, if you want to know the details, you can look at the paper or talk to me. But the main idea is the following. If we go for this A equals B version, so we only have two parameters, let's say S are the scores coming out of my naive Bayes. So this is the scores that I want to calibrate, okay? How could I implement this? Well, I take the scores coming out of naive Bayes, S, I convert it into log odds, essentially, a logarithm of S divided by 1 minus S, which is just a standard operation. That gives me one new, so I treat this as a new feature. So now I have this score S prime, which is a log odds, so it is something on the real axis. And I have the classes, so I just train univariate logistic regression on that. And the parameters that I get from that are exactly the parameters that I need here. And the reason that this works is because beta distribution and normal distributions are both members of the exponential family. So we essentially use a trick there to map one member of the exponential family to another. If you want the full A not necessarily equal to B, so the full three-parameter version, what you do instead of getting one feature out of the scores of naive Bayes, you get two features out of it. One of it is the logarithm of the naive Bayes score, and the other one is the logarithm of 1 minus the naive Bayes score. And then you fit bivariate logistic regression to that, and then you have the three parameters that you need. So this was a really nice realization that we could do it in this way, because we just piggybacked onto scikit-learn logistic regression, and we didn't even have to implement a new algorithm there. Okay, so that's the story with beta calibration. And the NeurIPS paper that we have in December is about extending this to multi-class classification. If you know your stats, you won't be completely surprised that this results in Dirichlet calibration, because then within each class you have vectors of scores, and these vectors within each class are assumed to follow a Dirichlet distribution, which is the multinomial extension of the beta distribution. Okay, very happy to discuss that offline if you're interested in that. Okay, moving on to a slightly different topic, and this is the topic, okay, what changes if I'm interested in F-score, F-measure, rather than accuracy? Now, when people use F-score, So F-score is the harmonic mean between of precision and recall. Now, I won't try that out here, but with my students, I would then ask, why the harmonic mean? Why not the arithmetic mean or the geometric mean or the quadratic mean? And there's usually a big silence. Well, that's just because that's what people do in the literature. Okay, there's a reason for it, and I'll give you the reason. But that's point number one. So, you know, people sometimes apply measures without really knowing why this one and not the other one. Then often I see as a justification for the F-score that people say, my classes are unbalanced, and so accuracy is bad for unbalanced classes. This is true. The latter bit is true. Accuracy is bad for unbalanced classes, right? So, you know, Google, if Google wants to evaluate its search engine, let's say just talk about the first page, for example. So Google gets money for putting results on the first page that you're actually interested in. Google doesn't get money for not putting results on the first page that you're not interested in, right? And accuracy would measure that, right? So accuracy, oh, you did really well. There are about X trillion pages on the web, and 99.99999% of those you didn't return in your search query. Really well done on the negatives. Of course, that doesn't make sense. You are swamped by the negatives, and accuracy. If Google would optimize its search engine for accuracy, it would never give you an answer to any query because, oh, it does so well on the negatives, right? So that clearly doesn't work. But if it's just a matter of class distribution, there are very easy fixes, right? So I could, for example, just take the average of true positive rate and true negative rate, right? So immediately I take the class distribution out of the equation and I separately measure performance on the few positive and separately measure performance on the many negatives and then take an average of those two things and the problem goes away. So the real reason why people use F-score is not class imbalance. It is that true negatives, only the true negatives don't add value. That's the real reason, okay? So the F-score, so here is kind of hidden in this slide are answers to some of the questions that I raised. So F-score is the harmonic mean between precision and recall, which you can write like this. If you expand the definition of precision and recall, then you get something like this. Now, this is the equation of interest, because so precision is true positive divided by true positive plus false positive. Recall is true positive divided by true positive plus false negative. So the common form that they have is true positive divided by true positive plus mistakes. And the mistakes are different in each case. So what F-measure simply does is take the arithmetic mean of the mistakes that you make. Yeah? So if you want to combine false positives and false negatives, let's just take the arithmetic mean of the two of them, stick it back in that general formula, and that gives you the F-score. Okay? And to me, this is a sensible thing to do because counts in a confusion matrix are kind of additive. You don't multiply those, you don't divide those, you add them up. And so using the arithmetic mean here makes sense, but because you're in the denominator, that translates to a harmonic mean there. So this would be my justification for why you use harmonic mean on the level of precision and recall. Now the second thing is, and people often think, hey, Peter, there's a mistake in your confusion matrix here. There's a deliberate mistake here. So F-measure can be understood as accuracy in a modified confusion matrix. So normally you have the good guys in blue and the bad guys in red. So you have true positive here, and normally you have true negatives here. You have false positive and false negative here. But Google doesn't make money on true negatives. Yeah? Google doesn't make money on non-answers that are correctly not returned. So we want to take this guy out. One thing that you could do is set this to 0, which effectively leads to the Jacquard index, intersection divided by union, true positive divided by true positive plus false negative. What F-measure does is actually if you multiply everything by 2, then you get 2TP divided by 2TP plus FP plus Fn. So actually, F measure effectively sticks another copy of the true positives here. And then in this table, the accuracy in this table is the same as F measure. OK? Statisticians hate this because I'm messing with the marginals here. Now, that means I'm changing the class distribution because this number changes. And that changes depending on how good my classifier is. So for each operating point, I'm kind of changing the class distribution. So statistically, this is horrible. But pragmatically, I think there are reasons for doing this. So because of this, we wanted to analyze what the what the consequences of that are. And so when people do this kind of analysis, so who of you has ever drawn a precision recall curve? OK? How do you do that? Just draw precision on the y-axis and recall on the x-axis. Calculate the area under the curve, maybe? Yeah, OK. I'm sorry, all these things are bad. Excellent, good. OK, I'll tell you why. So there's a couple of issues with this. Some of them subtle, some of them not so subtle. But the main issue is that because we have this harmonic mean in there, things are not linear anymore. So linear interpolation in precision recall curves is problematic, and calculating the area under it is problematic as well. So before I go on to that, let me just briefly go back to my ROC curves and say, why is F-score different from accuracy? Well, remember we had these iso-accuracy lines, which are these lines with a particular slope, which derives from the class distribution, and you want to be as close as possible to ROC heaven here. F-score isometrics behave differently. They kind of rotate around an imaginary point here outside of ROC space. And that point depends on the class distribution. So basically, I now have, so for instance, this point has this F measure isometric, this point has this F measure isometric, this point has this F measure isometric, and we want to be as high up as possible. So in this situation, this would still be the optimal point. OK? But it's different from accuracy, and therefore, calibrated probabilities, calibrated in the previous way, don't work for F measure. OK? This has been recognized many times, and there are different solutions for it. But I think we have kind of a more fundamental solution to this. And here is my answer to how to do this. So basically, I want these scores to tell me where to put the threshold. And so if I put the threshold at 1/2, then I know that my operating point should be, I should label these two as positive and this one as negative. OK? So I want the scores to tell me which point to take. OK? And for example, if a segment is on the decision boundary, I want that segment to have a score of 1/2. But I can't use the scores that I used previously. Again, I don't have time to go through the details, but essentially, a score calibrated for F measure looks like this. So I basically take a difference of this ratio in one point and this ratio in the other point. And then I take a difference of this ratio as well. And that will give me my calibrated score. This is not obvious at all. I'm very happy to talk about how we got to this result. But let me just talk you through a couple of calculations. So this is actually the same formula, but in an easier form. And it avoids dividing by 0 and so on. So in this case, let me look a little bit at, so threshold 1/2 gives me this as an optimal point. And indeed, if you do the calculations, the F1 score here is optimal. So how do I get these numbers in this case? So for example, if you look at if you want to calculate this score, then basically you are looking at the differences between these ones. So we're doing false -1 times true +2. So that is 4 times 8 is 32, minus 2 times 6, 12. So that's 20 here. And then we take the difference between these two. Then we have 3 times 8 is 24. Minus 0 is 24, so 20 divided by 24 is 5 divided by 6. So that's how I got that number there. Okay. Interestingly, this number will always be 1. Why is that? Well, we can do the calculations. Basically, here we always have that TP1 is 0, so these terms disappear. And we also have that FP1 is 0 always, so this term disappears, so I get this divided by itself is 1. What that means is that for F-score, it is never optimal to go below this point. So low recall points are never optimal. Yeah? It only starts becoming reasonable once you get to this point. This is different from accuracy. So sometimes when you have enough negatives, always negative classifier is optimal. The always negative classifier is never optimal for F-score. Okay? So that's kind of a little thing that follows from this analysis. So if we change the numbers a little bit, so in this case I have made 5 copies of all the negatives, and then it all works out. This segment becomes on the decision boundary, gets score 1/2, meaning it doesn't matter whether you choose this operating point or this operating point, you get the same F-score. Okay? People could do this before, but they had to do all the calculations here. Now that I have the calibrated scores, I just have to look at the calibrated score and say, oh, this guy gets 1/2, so it will be on the decision boundary. Okay? It doesn't matter how it is labeled. Okay, so going a little bit further about the curves. So on the left is a ROC curve. On the right is a precision recall curve. It's not very easy to see, but there are, so the blue dots are basically the ROC curve, or a curve is really a selection of points. The red circles are points that are on the convex hull, so they are like on the Pareto front, if you will. With the dotted red line interpolating there. There's a point-to-point correspondence between ROC space and precision recall space. But as you see, kind of, it's not actually that obvious in precision recall curve to find which points are on the Pareto front. That's certainly not easily done by visual inspection. And the reason for that is that because interpolation is hyperbolic in this space and not linear. So I won't go into details here because of time, but ROC curves have lots of nice properties, which is why people think, well, if I then just change the axes a little bit and get precision recall curves, maybe I inherit those nice properties. Actually, none of those properties hold for precision recall curves. Everything is problematic in precision recall curves. For example, going back to here, I didn't indicate that, but there's a non-reachable area here. So there are certain precision recall, certain combinations of precision and recall here that are unachievable. This point depends on the class distribution, so how far you go down here. This is precision at 100% recall is the proportion of positives. Okay, which depends on the class distribution, obviously. So if I combine two PR curves with different class distributions, it doesn't mean anything because I'm comparing apples and oranges. Right. So graphically, I'm going to show you now essentially what we're doing. We're fixing this by, so here's the PR curve with some extra line. This is the precision recall break-even line. Obviously. This is an F-score isometric, and this is actually the F-score isometric of the always positive classifier, because when you do F-score, the always positive classifier is the one to beat. Not the random classifier or the majority class classifier, but the always positive classifier, because you get that for free. So you should never accept an F-score that's lower than you get for free from the always positive classifier. So that guy is here. And what we've done is we've linearized everything so that effectively we're pulling everything up such that this line becomes this diagonal. And now suddenly the whole thing looks more or less like a ROC curve. I have linear interpolation. It's clear from visual inspection where the Pareto front is. The area under this curve is meaningful. And also I can calibrate. So I already showed the calibration here, but here is another example. So for example, if I calibrate, so here calibrated scores with the ROC curve, here are calibrated scores for a precision recall curve. As you see, this segment here has a score very close to 0.4 to 1/2. So these numbers tell me, just without any more work, that if I'm interested in F1, so equal weight of precision and recall, then these 2 points will give me almost the same performance. Actually, strictly speaking, this one should be chosen because this slope is slightly below 1/2, but I can just see from this curve and these numbers that this is the optimal point for F1, and this point is only very slightly worse. Okay? And that's not something that other methods will give you. So what the upshot of this is that I think we need to get used to the idea that our machine learning models should output more numbers, more things. There's no reason why a classifier can only ever output one number. Okay? So my classifiers output a calibrated probability if you're interested in accuracy, and a different calibrated probability if you're interested in F-score. These two numbers are not reducible to each other, so I need them both. And so now the user can decide, today is Monday, I'm optimizing accuracy, I use this number. Tomorrow is Tuesday, I'm optimizing F-score, I use the other number. And maybe there are other evaluation metrics, non-discounted, normalized discounted cumulative gain. Don't get me started on that one. I think that's a big hack, but maybe I shouldn't say that in this community. But I'd be very happy to have an offline discussion about that. But if you want to optimize for that, maybe there is a different calibration procedure and your classifier outputs a third number because on Wednesday you're interested in optimizing NDCG. Okay, so that's the picture here. So let me, oh, and by the way, if you're using area under precision recall curve as an evaluation metric, which, for example, the Pascal challenge did all those years ago, these things matter. Because here is an actual example where the dotted line has a higher AUC because it's higher here and higher there and a bit lower there. It has a higher AUC, so if you optimize for AUC, you would choose the dotted line. If you optimize for precision recall, you would still use the dotted line, area on the precision recall curve. If you optimize for area on the precision recall gain curve, curve, then you would choose the solid line. And why is that? Because actually a lot of the advantage of the dotted line is at low recall. And that is the area where you're under this you know, the performance that you get for free is the yellow line. So it doesn't really matter that you beat somebody under that line because that bit disappears in our curve here. Because you're not really interested in that. So you're rewarding a model for outperforming another model in a part of the space that you're never going to be interested in because, you know, it's not relevant. So sometimes these things really matter and you get a different ranking in performance if you change to what we think is the right way of doing things. Okay, I'm going to very quickly wrap up. So I think performance evaluation in machine learning and maybe also in recommender systems is fraught with issues. It's a bit surprising given that we've been doing this for donkey's years, but there are lots of things that people do because other people did them. And so, you know, by induction, we will do the same thing forever. So everybody, myself included, if we submit the machine learning paper, we include the big table with, you know, as many data sets as we could and comparing against competitors and AUC and accuracy and all these different metrics. We need to stop and think about this because this is getting a bit silly. We don't really understand those metrics. We don't really make the case that those are the right metrics in our application. And so there are lots of issues here. So, where I take inspiration is 3 areas. So one of them is that there is an area called measurement theory, which talks about scales. So measurement theorists love doing these things. I have a rigid rod of length A and another rod of B, and if I put them next to each other, what can I say about the combined length of these rods? Well, you say it's obvious. It's the length of A plus the length of B. But you know, mathematicians would say there's an operation of concatenation, and then there is some and then there's a measurement function, and then there is some kind of mathematical operation here, and somehow you want this to be an isomorphism of some kind, okay? And there's a lot of things that you can say about this. So, for instance, there are these 3 volumes of foundations of measurements, volume 1, 2, and 3, and these are, you know, Patrick Sippes, Kranz, Tversky was mentioned yesterday. He is authored on some of these. So there's a lot that you can say, and I think we machine learners need to take inspiration from that. So in what way? I'm going to skip this. This was a lovely audience participation question, but I'm going to skip this. There is this notion of concatenation. So there are natural notions of concatenation in confusion matrices. So suppose that this is one confusion matrix, and this is another confusion matrix. We can somehow concatenate them, which would mean a cell-wise addition or maybe a cell-wise averaging. So if I do averaging in my rock space, I end up here, and simply all the numbers in this table are cell-wise averages of that table. So now a reasonable question is, I can evaluate accuracy in this table and accuracy in this table and accuracy in this table. So a measurement theorist would ask the question, what can I say about accuracy in this table related to the accuracies in this table? Now, if you think about it for a second, you realize that accuracy in this table will be the average of the accuracies of that table, only because I made the sample sizes equal. So if the sample sizes are unequal, I probably need to take a weighted average. Okay? What about true positive rate and false positive rate and so on? Well, they can also be averages, assuming that the class distribution is the same in both cases. So if the class distribution is not the same, then I need to compensate for that. This is one reason why people do stratified cross-validation, because then I can simply average the true positive rates that I get. But this story doesn't hold for precision, and it doesn't hold for recall. Sorry, it holds for recall, but it doesn't hold for F-measure. So the only sensible way to average F-measures in these guys is if we make sure that the column marginals are the same in each table, so that the 2 points make the same proportion of positive predictions, which is quite a different thing from saying, well, I'm going to divide my data set such that I get equal class distribution. It's very different to say, I'm going to divide my data set such that my classifier makes the same percentage of positive predictions. And of course, that depends on the classifier. So there clearly is a story here. So that's ingredient number 1. Ingredient number 2 is that we need to learn from psychologists, because psychologists have realized that if we want to assess somebody's ability, we can give them an exam, okay, and we can see how well they do in the exam. But the performance on the exam is at best a noisy measurement of true ability. You know, that maybe they had 3 exams in that week, or maybe they weren't very well, or they missed half of the lectures, or whatever. So the right way that psychologists go about this with things like item response theory is to assume that ability is a latent variable, and difficulty of questions is a latent variable. And then we get observable performance, and then we make inferences about the latent variable given the observable performance. So what we do in machine learning is just do the big table and do the big cross-validation, and that is the ability of my classifier. And yay, all the numbers in my column are bold, so I beat everybody else. I'm the best in the class. But actually, maybe you gave it very easy questions, or maybe your questions were biased in some way, so that you anticipated that answer. So the second ingredient, I think, in performance evaluation is that we need to use latent variable models. And here is, I'm just flashing this slide. This is a paper that we did using a version of item response theory in machine learning. And this was published in AI Stats earlier this year. And again, I'm very happy to talk to you about it. But the key point is that we have observable performance here, but we also have these latent variables that are the ones that we're really interested in. So to give you a bit of the flavor, what we're trying to do here, so cognitive psychologists, they like to do things like adaptive testing. So if I want to test your ability, I'm going to give you a medium hard question. And depending on how well you do on the medium hard question, I'm going to give you a harder or an easier question. So I'm doing kind of a binary search in ability space. And so with maybe 5 questions, I have discretized ability space in 32 bins, which is probably OK. So rather than throwing 42 UCI data sets at my problem, I just want to choose 5 well-tuned, well-understood data sets that I know how difficult they are. So I do more SAT testing rather than just throwing lots of data sets at them, some of which, for instance, mushroom, which everybody uses. No classifier gets mushroom wrong. Stop using mushroom as a data set, because this is equivalent to me setting an exam question that everybody gets right. I'm just giving myself extra work. It doesn't make sense, right? So too hard data sets don't make sense. Too easy data sets. Yeah, I'm wrapping up. Sorry. OK, the third ingredient, which I don't have a slide on, is that we need causality. We need not to say algorithm A outperformed algorithm B full stop, and I win because algorithm A is mine. We need to say algorithm A was outperformed by algorithm B because the data was highly imbalanced. Or counterfactually, we want to say, if I were to remove the imbalance from my data set, the difference in performance would disappear. Right? That's a sensible thing to say. Then you say algorithm A, it still wins because it's better at dealing with imbalance than algorithm B. But we want to have a causal narrative there, I think, and not just saying, oh, here's a big table of numbers, and the bold numbers are all in the right column, so everything is fine. OK, so I'm going to stop there. So there's a lot of work to be done. Here are the things that I'm going to concentrate on in my research. And with such a great audience and such a varied set of backgrounds, I would be very happy to hear from your perspective on this, or if you think that NDCG is great and the best thing since sliced bread, I'm very happy to have that conversation as well. But thank you for listening. I'm very happy to take questions if we have time. Thank you.